Good morning, everyone. This is Mr. Couple. I'm here this morning with my physics class, and we're going to be starting the nuclear physics unit today. I have three main ideas for today's lesson. Is that the first thing I want to talk to you guys about is how big the nucleus of an atom is. I want to kind of go into the history of the discovery of the nucleus of the atom. We also want to talk about the nuclear force, which is the force that holds the nucleus together. It's the strongest force in nature. And then the last thing I want to talk about is what a nuclide is and how we make a symbol to represent each nuclide. So that's the plan. Let's begin. All right. So normally in class, I go into this whole like historical story, like talking about all the different, you know, people who made these discoveries and things like that. But we don't really have time to go into all of that. So I'm just going to basically just tell you guys what we discovered. So in the late 1800s, about like 1896, like the super late 1800s, in the last decade of the 1800s, it was discovered that uranium and other elements like thorium and radium, that they would spontaneously release particles. And these particles were called radiation. So here's a video of that happening. This is a sample of uranium. It's like right here in the center. There's a little teeny tiny piece of actually it's a it's I think it's lead actually, but the point is that there's this little sample of a radioactive material and you can see that it's shooting out these particles. Now the only reason you can see these particles is because this is a special device. You can see the glass edges there along the outside, like there's that device that's holding it in. What happens is that the inside of this chamber, it's called a cloud chamber, it's filled with alcohol vapor. And when these little particles of radiation, they're traveling at like 3% the speed of light. When they come like flying through the alcohol vapor, they leave a little trail behind that lets us see where they are. So this is a device called a cloud chamber, and it's what allows us to be able to see radiation. Even though it's invisible, we're seeing the trail that it's creating. So this was a discovery. It was a huge discovery that there are certain elements that seem to just spontaneously shoot out particles from them. And those particles, that's what's called radiation. So it was very quickly discovered that there were three distinct types of radiation that were discovered, and they were named alpha, beta, and gamma, which are the first three letters of the Greek alphabet, and they're just using those in order that they were discovered. So first we discovered alpha rays, then we discovered beta rays, and then we discovered gamma rays. So to test the properties of these different rays, what you would do is inside that cloud chamber is you would stick electrically charged plates. And so that's what we're seeing here, like these little parallel plates here. And so that's creating an electric field. And so you're sending these particles through the electric field. And if these particles have a charge, then the electric field is going to exert a force on them. And that's what's causing these betas to bend upward and the gammas to bend downward. So based on this, you guys that are listening, if you want to, can you say what the charge of a beta ray is? So given that the beta ray was attracted upward, what's the charge of a beta particle?
Negative.
Negative.
Exactly right, because it's attracted to the opposite positive charge. And then from this, we can see that alpha rays are positively charged. And then what about those gamma rays that just went straight through without any force exerted on them? They must be
Neutral.
they must be neutrally charged. And so we were able to find these three distinct types of radiation by sending them through electric fields. One thing that's important over here is notice that the radioactive substance is here, and what it's really trying to do is it's trying to shoot out radiation in all directions, like that video I showed you. But we've entombed it within this lead block, and the lead block has an opening at one end, and so it basically creates like a stream, like this beam of particles that go boom. So none of the other particles can make it out this way. They just end up getting blocked by the lead, and lead can actually absorb almost all types of radiation. That's the next thing. So the three distinct types of radiation, alpha, beta, gamma, they also have varying penetrating power. So you can see that alpha particles are stopped even by something as thin as a piece of paper. Beta particles can get through paper, but they can't get through metal objects like conducting materials. And in gamma rays, most gamma rays are blocked by lead, but the really high energy, like super powerful gamma rays, can actually even penetrate through lead. But you can see that most of the gammas are getting blocked by the lead, but some of them, like the super high energy gammas, can actually even get through lead. The sample that we have inside here is not emitting that powerful enough gammas, so otherwise we would be detecting gammas out here, and we're not. The lead is absorbing it. Do you guys have any questions for me about the penetrating power or like any of this radiation stuff right now? Like what questions do you have?
Why does this happen? Like, why are gamma rays stronger than, like, is it that they're higher frequency or higher
It's
energy?
well, it's what they're made of. So gamma rays are made of photons, And so photons are particles of light, and they don't really they interact with electromagnetic fields, but when they're really high energy, they can just like punch through anything. They're basically electromagnetic waves, but we learned in the early 1900s that electromagnetic waves are actually made of particles called photons. I'm not really going to go too much into that stuff. Beta rays are electrons, and so that's why they're absorbed by metals, because they just become currents within the conducting surfaces when they hit it. And then the alpha is a helium nucleus. This wasn't discovered until way later. So we knew that there were three types of radiation, but we didn't know what they were. We have since discovered that, the reason why the reason why alpha gets absorbed by paper is because it's this big honking fat helium nucleus, whereas the beta is a little teeny tiny electron, and then the gamma is actually photons. And photons don't really interact with matter, so they just like pass right through it. Hopefully that answers your question. All right, I said I was going to avoid talking about history, but I have to mention these three individuals because they made one of the most important discoveries in nuclear physics, and that is they discovered the nucleus. It's called nuclear physics because it's the physics of the nucleus, so we need to talk about the people who discovered the nucleus. So the two people that discovered it were Geiger and Marsden. They actually performed this experiment for their graduate studies. So their professor was Rutherford. He was their advisor, and so Rutherford sort of gave them the idea and said like, "Hey, go do this experiment," and then they went off and they conducted the experiment. Rutherford is credited with the discovery of the nucleus, but the data was actually painstakingly collected by Geiger and Marsden, which is why I'm giving credit to them here. Here's the experiment. So what they did was they took a really teeny tiny thin piece of gold foil. It was 10 atoms thin. So from one end of this piece of gold foil to the other, only 10 atoms across. It was really, really small. And then they had that source of alpha particles. So they wanted a material that was just shooting out alpha particles, and it's very similar. You have this lead block, the sample encased inside, so you're creating this red line is a beam of alpha particles, come flying out of this source, and so you're going to shoot it into the gold foil, and we're going to see what happens. So out here on the side, they have this little, it's called a microscope, but there's a little plate on it called a scintillator. And what happens is when a radiation hits a scintillator, it releases a flash, like a little like a spark of light. So that's called a scintillation. And so what Geiger and Marsden needed to do was they needed to put their eye in this microscope, and then you can see another picture here. So they had to look through here, and then they would have to bend over and hunch down and look through this telescope or microscope, and they would look to see the scintillations, and they'd have to manually count the scintillations that they see. And it's even more difficult than that because they didn't just do it at one angle, they did it at like a whole bunch of different angles. So they would change the angle, and at each angle, they'd count how many scintillations, how many scintillations, how many scintillations, how many flashes of light, each flash of light meaning they've detected a particle. And so what they're trying to do is they're trying to see, well, how do these alpha particles behave? Like how if we found that like radiation can like penetrate into matter, well, let's use these alpha particles like bullets that we can shoot at the gold foil. And so this is what they were sort of thinking was like, if we bombard this piece of gold foil, so here's just one layer. This is just one layer of atoms inside the gold. Now imagine there's actually 10 of those. And so what they're doing is they're just pew, 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 like shooting these alpha particles at the gold, and they're looking to see what happens. And so you can see that most of the time, when the deflection angle was low, and by deflection angle, we're talking about like this angle here. So as long as they kept that angle, theta is the symbol used for angles in math and science. So as long as the angle was low, they found a lot of alpha particles. They detected a ton of alpha particles going through at these angles like this. But they found very few alpha particles at these higher angles and only like a teeny, teeny, tiny amount of them coming back. But that was shocking because these alpha particles are traveling at 3% the speed of light. That's insanely fast. And they actually found some of them that were reflected off the gold foil, which is nuts because there's like this tiny little 10 atom thin piece of foil, and these particles that were traveling at 3% the speed of light actually bounced off of them. And this is a shocking result. So it turned out that it was only 1 in 8,000. So 1 in 8,000 bounced off the gold. And so this was a startling discovery. And it raised a lot of questions. So this is what they were thinking. So if most of the alpha particles pass through with very little deflections, like a knife through butter, they're pretty much just go straight through. how could so few of them recoil like rubber balls from a stone wall? So that's what they're thinking is like, how could it be that almost all these alpha particles go straight through, but then just a tiny few, like a teeny, teeny, tiny few of them actually bounce off? And they had to answer this question, and it was Rutherford who answered this question. So this is what, so this is sort of the idea. So we expected that the alpha particles, these are the alpha particles being shot in here, that the alpha particles would just go straight through, but that's not what we saw. We actually ended up seeing some of them get deflected. And so after a series of calculations, Rutherford made the following conclusions. He said, the nucleus has a positive charge because the alpha particle has a positive charge. So we talked about that. I'll show you guys again up here. So the alpha particle has a positive charge. We knew that. And so if an alpha particle is bouncing off the nucleus, then the nucleus must have a positive charge because like charges repel. The second conclusion is most of the mass of the atom is concentrated in a tiny nucleus. So instead of the mass being spread out across the entire atom, the mass is concentrated in this center point called the nucleus. And then the last thing he figured out was the actual diameter of the nucleus. And so the diameter of the nucleus, like measured from one end of the nucleus to the other, is actually 100,000 times smaller than the diameter of the entire atom. And so those are his three main discoveries. Was first, he discovered the nucleus, obviously. It has a positive charge. It's a tiny, tiny dot at the center where all the mass or most of the mass of the atom is concentrated. The electrons are kind of just like this fluff that just fluffs around the atom. But the atom is mostly made of this teeny tiny nucleus. Now, how big is that nucleus? Well, this is the currently accepted model of the atom. It's called the electron cloud model. It comes from this equation in quantum mechanics called the Schrodinger Equation. Just thought I'd show it to you guys. You can take a look at what some advanced physics looks like. So if you crunch the numbers through this equation, you find out that the electrons actually don't really have a physical location where they exist. They kind of exist across this like spread out distribution called the electron cloud. And the nucleus is crazy, crazy, crazy small. So this unit here is called the femtometer. Femtometer. And a femtometer is 10 to the negative 15 meters. So it's incredibly small. And then the nucleus itself is 100,000 femtometers across. The atom, its diameter is 100,000 femtometers across. So the nucleus is incredibly small. Like if I wanted to draw a picture, like, hey, okay, here's this circle. How big is the nucleus? Like most of the time you'd see it drawn like that. That's completely wrong. In fact, if I wanted to draw the nucleus, and if this was the actual size of an atom and I wanted to draw the nucleus, it would be smaller than a pixel. Like I wouldn't be able to show it to you. It would be smaller than a pixel on your display right now. You wouldn't be able to see it. The nucleus is incredibly, incredibly small. And Rutherford figured that out by looking at this data and seeing how many alpha particles pass through at each angle. And he was able to do the math and calculate the size of the nucleus based on that. We do the math in my IB physics class, if you guys are interested. Okay, where am I? Okay, cool. I'm going to stop for questions.
No questions from me.
What do you guys think? Like,
No questions.
what's your reaction to this? Because this should be like mind-blowingly awesome.
This is a perfect example of how grad students get screwed over in research.
It really is. You nailed it. That's why I mentioned it to you. Academia is a rough business. Yeah, so the thing that's like just completely insane to think about, right, is like we are made of atoms. Like everything is made of atoms, like all stacked together, like forming bonds. But the mass of the atom is actually this teeny tiny spot in the center. And so most of what you feel and interact with, like around you, like if you take your hands and push them together, you're not actually feeling the matter. You're feeling the electric fields of the electrons that are out here in the cloud. You're feeling those electric fields repelling each other. You're not actually feeling matter. You're actually feeling these electrons fields repelling each other. And that's kind of crazy to think about.
We have a natural force field.
We do. So when your sense of touch, this is going to segue really well into here. Your sense of touch is derived from the electromagnetic force. You're feeling the electric fields that the electrons are creating outside on the edges of the atoms. So when you touch things, your sense of touch is an electromagnetic response. So here's a question. If the nucleus is positively charged, right? So the nucleus consists of these positively charged particles. Then what is preventing the nucleus from ripping itself apart? Because positively charged particles repel each other by the electromagnetic force. So what's preventing this proton here and this proton here from repelling each other? Like, why isn't the nucleus just ripping itself apart? Do you guys know?
Nuclear force, right?
Exactly right. So there's a new force. It's called the nuclear force. So here's our picture of like the forces that we've studied so far this year. So we've got the electromagnetic force, which we just spent a series of videos for the past 4 weeks on. The electromagnetic force is a force that acts between charged particles. In this case, protons repel each other. It has an infinite range, and its relative strength is about 7 thousandths of the relative strength of what I'll show you in a second to be, well, I'll just show you now, which is the strong nuclear force. So if we say the strong nuclear force, that its strength is 1, we'll just randomly just say 1. Then the electromagnetic force, the strength would be 7 thousandths as much as that. So the electromagnetic force is more than 100 times weaker than the strong nuclear force. The strong nuclear force is the strongest force in nature. And then you can see where gravity stacks up here. I always tell you guys that gravity is an incredibly weak force. You can only notice it when you have huge masses involved. Well, if you calculate the gravitational attraction between two protons, it ends up being a ridiculously small number, like incredibly small. So it can't be gravity that's holding the nucleons together. Gravity is just at this scale, at these like amounts of mass, which like a proton has, gravity just isn't even felt at all. And in fact, all of the currently accepted models of physics completely ignore gravity within the quantum realm or within this scale of looking at things. We don't even account for gravity because it's such a small force. Okay, so the strong nuclear force, let's talk about it. So the strong nuclear force, it's an attractive force between nucleons in the nucleus. So what happens is the electromagnetic force is trying to pull apart the nucleus, and the strong force is like these bonds between all the nucleons. They all stick together because of the strong force. Whether it's a proton and a proton or a neutron and a proton, all the nucleons are all kind of stuck to each other by this nuclear force. So that's the nuclear force. So
Are nucleons the source of the nuclear force?
no, it's actually quarks, and but nucleons are made of quarks. I'm not going to talk about quarks, but that's the source of the nuclear force. It's actually quarks. We'll talk about it in IB physics. The way to think about the nuclear force, this comes from Carl Sagan, who's a famous science communicator and scientist, astronomer. So he said, think of the nuclear force like short-range hooks. That the nuclear force, if you get nucleons close enough together, they can hook together and get stuck to each other. But if they're far apart, they don't act. And so that's the thing about the nuclear force, is it has an extremely short range. It only goes about 3-ish femtometers. So it's a really short range force. Whereas the electromagnetic force and gravity, they don't have a range. They go out to an infinite distance. So the strong nuclear force is the strongest force, but it has a weakness, is that it has a very short range. Check out this graph. So the strong force is actually super complicated. Like it's not as simple as like an inverse square law or, like mm over r squared or qq over r squared. I can't even show you the equation. It's too complicated. But the nuclear force basically works like this. If two nucleons attract each other, then why don't they actually like collapse into each other? Well, it turns out that once the nucleons actually go inside of each other, so once they actually enter each other, they actually the strong force becomes a repulsive force and it pushes them back out again. But then when they get far apart from each other, it pulls them back in again. And so then so the strong force sort of has these 3 ranges where like at very short range of less than a femtometer, it's repulsive. But then in this in-between range of about 1 to 3 femtometers, it's attractive. But then if you go too far away, if you go further than 3 femtometers, it just completely vanishes. It doesn't exist. So those are the properties of the strong force. It's extremely strong when it's holding nucleons together, but if you get too far away, it'll get really weak. This answers the question, why is the nucleus so tiny? Because the strong force has such a short range. The strong force is the force that holds the nucleus together, but because of its extremely short range, the nucleus can't be bigger than a femtometer-ish, like, a dozen femtometers. Like, it can't really get larger than that. And so that's why you don't see nucleuses that are big, because the force that holds the nucleus together doesn't act at those long ranges. So it cannot hold the nucleus together. Inside the nucleus of the atom, the two strongest forces in nature are pitted against each other. So there's this battle. It's the strong force trying to hold the nucleus together against the electromagnetic force that's trying to rip it apart. So just to recap, the strong force acts on nucleons. It's the strongest force in nature, but it has a very short range. The electromagnetic force acts on charged particles, protons in this case, that are in the nucleus. It's 100 times weaker than the strong force, but it has an infinite range. State how the following nuclear changes affect each force. All right, so what happens if the nucleus gains a proton? What will happen to the strong force? What do you guys think? Nucleus gains a proton. Will the strong force get weaker, stronger, or no change? Are you guys still there?
I don't know. How does it change, Mr. Keppel?
A proton,
Stronger?
yeah, a proton is a nucleon. It's going to get stronger. If you get more nucleons, you get more strong force. Okay, what about the electromagnetic force? A proton is also a positive charge.
So it gets stronger as well.
It also gets stronger. So if you add a proton to a nucleus, both these forces get stronger. Okay, what if you add a neutron?
Weaker?
So strong
Nu-
force. We'll do the strong force first.
Strong force gets stronger, right?
So a neutron equals a nucleon. So yeah, strong force gets stronger. But a neutron has no charge,
No charge.
which means the electromagnetic force
Doesn't change.
yeah, there's no change. The electromagnetic force stays the same. So if you want to strengthen like the stability, like how well a nucleus is held together, just add a neutron. If you add a neutron, the strong force gets stronger without increasing the electromagnetic force. The electromagnetic force, remember, is trying to pull apart the nucleus. The strong force is holding it together. Just moved my camera. That's funny. So the electromagnetic force is trying to pull it apart. So you wouldn't stabilize a nucleus by adding a proton, because that would make both forces stronger. You'd stabilize a nucleus by adding a neutron, because that would allow the strong force to get stronger without strengthening the electromagnetic force, which is trying to pull it apart. Okay, what happens if we deform the nucleus and like stretch it out more? So like here's a picture of a nucleus that has been, stretched out. So what'll happen to the strong force if we stretch out the nucleus?
It'll get weaker.
Yeah, it'll get much weaker. And that's because at large distances, the strong force goes away. What about the electromagnetic force?
Stay the same.
It'll get a little bit weaker. The electromagnetic force gets weaker with distance, just like gravity, 1 over r squared, inverse square law. But it has an infinite range. So the electromagnetic force can go forever, but the nuclear force can't. The nuclear force gets cut off after 3 femtometers. And so if we go too far, the nuclear force will no longer be able to pull these parts in. It won't. But these parts will still be repelling each other. And so what happens if you deform a nucleus? What happens is this: the nucleus splits apart. The nucleus will rip itself apart if it gets deformed too much. So this is called nuclear fission. So that's what I've been talking about up there, is if a nucleus gets deformed, in this case, a neutron is sent at the nucleus and boom, like whacks into it, and then it deforms the nucleus until the nucleus splits apart into 2 pieces. So that's the way of splitting a nucleus. It's called splitting an atom. You guys have probably heard of that before. But really, when you split an atom, you're just breaking apart the nucleus into 2 smaller pieces. It's called fission because it sounds like division. Another thing that can happen when the nuclear force loses is if it loses by just a little bit, you get alpha decay. If it loses by a lot, like where you're deforming a nucleus, like boom, in a snap, the nucleus will rip apart. But if it just loses a little bit, you'll get what's called alpha decay. And notice that's an alpha particle being shot out of a nucleus. And so that's what's happening when a nucleus is radioactive. It's because the strong force isn't strong enough to keep the nucleus together, and an alpha particle gets spat out of the nucleus. All right, so what we need is we need a way of keeping score. Like we need a way of saying which force is winning. Like is it the strong force that's winning or is it the electromagnetic force that's winning? We need a way of telling like how the stability is, like whether the nucleus is going to hold itself together. And to do that, we come up with this thing called nuclear notation. And so this is what my plan for the last 5 minutes or so of this video is to show you guys how to write down this notation. So first of all, I want to tell you guys what a nuclide is. So nuclide is a distinct nucleus, which means there's only one nucleus like this, and it has a specific number of protons and a specific number of neutrons. So this information, the A and the Z, is going to tell you how many protons there are and how many neutrons there are. And then this X is just some letter that you're going to use to name the element. Like hydrogen is H, helium is He, carbon is C, nitrogen is N. And then you're probably familiar with some of those. I think they taught it to you guys in 8th grade a little bit about the different chemical symbols. Okay, let's start off with Z. So that's the number that goes on the bottom. Z is called the atomic number. It's weird. It doesn't make sense why it's a Z. But the atomic number tells you how many protons there are. A lot of times you just call it the proton number. Like a physicist would just say proton number. But a chemist would be, what? That's the atomic number. So Z is the atomic number. The reason you call it the atomic number is because it's used to distinguish between different elements. So you can see in the periodic table, the number that's given here, 5, 14, 33, like all these numbers, these are the atomic numbers. So the atomic number of fluorine is 9. The atomic number of oxygen is 8. What that number is telling you is how many protons there are. So if you have a nucleus that has 16 protons, that's called sulfur. If you have a nucleus that has 54 protons, that's called xenon. And so that's the way it works, is that Z tells you the name of the element. It tells you it's why it's called the atomic number. The mass number, which is A, so that's the one that goes on top. So the mass number A is called is how you tell apart. It's like how much mass there is. So it's like how you tell apart different isotopes. So an isotope means it's the same element. Like all these guys have one proton, but so they all have one proton. Notice they all have one for the atomic number, but they all have a different number of nucleons. This one has one nucleon. So protonium has one nucleon, two nucleons, three nucleons. And so those are called isotopes of hydrogen. They all have a different number, a different amount of mass. And so that's what the number on the top tells you, is it's the mass number because it tells you how many nucleons there are. All right, so let's practice. So give the nuclear notation for each nuclide. All right, so remember, it's A on top. That's all of them. That's protons and neutrons. It's the number of nucleons. Z is the number of protons. And then the symbol is X. Okay, here we go. So first up, let's do this. So we're going to count how many nucleons there are. There's one nucleon in this nucleus. And how many protons are there? There's one proton. And this is hydrogen. Now, how did I know it was hydrogen? Well, I kind of have it memorized, but actually there's this handout I was gonna give you guys. So if I go in here to physics, nuclear physics, it was this table of elements. So this is the handout that I normally give students during the nuclear physics lesson unit. It's like your cheat sheet, I guess. Come on, load. It takes forever. Come on, you can do it. Okay, here we go. So there's just a table of elements, and so what you do is you just go look up. It's sorted by atomic number, and so I just look for number 1, and number 1, atomic number 1 is hydrogen. So that's how I knew that this was hydrogen. If I go to the next one, okay, how many nucleons are there here?
2.
There's 2. And how many protons are there?
1.
There's 1 proton. And so once again, which number tells you which element it is? Well, it's the atomic number. So this isn't helium because helium has 2 protons. This is still hydrogen because it has 1 proton. So this is still hydrogen. But if we move over to the next one, now there's 3 nucleons and 2 of them are protons. And so now the atomic number has changed, which means we have a different element. This is now helium. Since helium has 2 protons. Helium has 2 protons. If we keep going, so this one has 4 nucleons, 2 protons. What is the name of this element?
Helium.
This is still helium because it still has 2 protons. And then this last one, let's see, 1, 2, 3, 4, 5, 6, 7, and then 3 protons. So this is the next element with 3 protons, and so that's lithium. So I write Li. So that's the basic idea of how the nuclear notation works, is you're just writing down two numbers. One of them tells you the mass, how many nucleons there are. That's roughly telling you how strong the nuclear force is. The more nucleons you have, the more nuclear force you have. And then the number 3 is telling you how strong the electromagnetic force is. And so that's sort of the way that we keep score, is that the mass number tells us the strong force. Come on. The mass number tells you the strong force, the strong nuclear force, and then the atomic number tells you how strong the electromagnetic force is. Okay, I think that's it. I guess I'm done. I have a few more here. If you guys want to stop the video now, go ahead and stop. I'm going to continue to solve these last two. If you feel like you need more practice on this, I'll solve these last two ones here. It says write the name of each nuclide below its symbol. Okay, so the way this works is, like, notice that both of these are fluorine. So how could we tell them apart? Well, this fluorine has 22 as its mass number, and this fluorine has 17. We have to show that these are not both just fluorine. We have to show that they're a nuclide, that they have a distinct number of protons and neutrons. And so the way you do that is you just put a dash, boop, and then write a 17 afterwards. Dash and 22. So these are called isotopes of fluorine. This is fluorine 17, and this is fluorine 22. And so depending upon that number that comes afterwards, you could actually reconstruct the symbols from that, right? Because that 17, the 17 here goes up there. And then the fluorine tells you that it's the number 9. So you could either write the symbol or you could just write the name. You'll see them kind of interchangeably used. So what would be the name of this nuclide?
Oxygen.
This is oxygen. That's the name of the element. The name of the nuclide,
22.
though, oxygen 22. And then this last one, this is, take a guess.
Sodium 17.
Sodium is Na. So Ne, if we don't remember, we can just go grab our handy table here. Let's see, Ne, there it is. So number 10, 10 protons, that's neon. So this is neon dash
17.
17.
17.
You got it. So that top number is the number that we put. So these are called nuclides, or you would say that this is an isotope of neon, or you can call it a nuclide. A nuclide is what physicists usually call it, and an isotope is what chemists usually call it. So when you guys take chemistry next year, you'll hear that word isotope pop up a whole bunch. And then this last one says complete the table. So if I give you the name, the symbol, or a picture, you should be able to draw all the other ones. Since it's a nuclide, it has a distinct number of protons and neutrons. So for hydrogen, I know hydrogen is H. The 3 tells me what number goes on top, and I know that hydrogen has 1 proton. If I want to draw a picture of this, I need to draw 3 nucleons, and I draw them all stuck together because the nuclear force is pulling them together. And one of them is a proton, and then the other 2 are neutrons. So you can put an N in there if you want to, or you could just leave it empty, or you could shade it in just to show that it doesn't have a charge. I'll do the shading in method. Okay, let's do the next one. So you guys tell me, what's the name of this nuclide?
Lithium.
That's the name of the element.
Lithium 6.
Lithium 6. So lithium 6 is the nuclide, because when you give that 6, you're telling it exactly how many protons and neutrons it has. If you just say lithium, you know how many protons it has, but you don't know how many neutrons it has. When I say lithium 6, I know that there's 6 nucleons and 3 protons, so there has to be 3 neutrons. So if I draw the 6 pictures here, 6 particles, 1, 2, 3, 4, 5, 6. Well, that's gross. Let me try again. So if I go 1, 2, 3, 4, 5. I can't make these fit. Whatever, 6. Okay, so then how many of those are protons?
3.
3. And so because we put that 6 at the end here, we knew how many protons and how many neutrons there were. There were 3 protons and 6 neutrons. That's what makes it a nuclide. It's called a nuclide when you actually know how many protons and neutrons there are. If you don't know, then it's called an element. So that's the element name, lithium. Nuclide name, lithium 6. This last one, we got to figure out what it is. So the first thing we do is you just count how many nucleons there are. So there's 1, 2, 3, 4, 5, 6, 7. And then of those 7, how many protons? 1, 2, 3, 4. And then we have to figure out what this is. So I'm going to look up on the chart. So which number do I look up to tell me the name of this element so I can write the chemical symbol? Do I look up
4.
7 or 4? You look up the 4. So let's go see. So 4 is beryllium. So I'm just going to write Be. Back to here. So this is Be. And then when I write the name, I write I don't remember how to spell it. Beryllium. Okay. Beryllium. Okay, that's the element name. So then the nuclide name is going to be beryllium-7.
7.
You guys got it. Okay, that's it. That's nuclear physics. You guys are now nuclear physicists. This is the introduction to nuclear physics. We'll be going more in depth as we go throughout the remainder of these. We got 2.5 weeks left. All right, thanks for watching, guys. Have a great day. I'll see you later.